Right, a bit of core further maths from vectors here. Yeah, got a bit of an issue. So I've got the FP3 international paper from June 2024. That's last year. The is this part of the question? No, it starts off sort of standard. It's got the one plane in this vector form. So the vector takes you onto the plane, and these two that take you around the plane. And then we have this other plane in the sort of the more standard R dot n equals d form. But then for part B, it says determine a vector equation for the line of intersection. Now, good luck finding an example of that in the textbook, because in the specification it talks about finding the angles between lines, angles between a line and a plane. It also mentions finding the intersection of a line and a plane, but it doesn't mention the line equation, the line of intersection of two planes. But on the mock paper, one of the mock papers they produced, there was an example of it. It's on the Core Pure one, the mock set that Pearson produced. So whilst the people in the textbook don't think it's on the content, Pearson clearly do. And they put it on the international paper, so it might be coming around the corner at us in England. So anyway, so here we go. Here's the question. I thought it'd be an opportunity for me to do some pretty pictures on my PowerPoint. So here's my plane with that vector equation. There's the origin. Now if I draw the 530 vector like this, so there we go, from the origin to that point. That's the point in the plane 530, where s is equal to 0 and t is equal to 0. So it's got position vector 530. And if I draw the 301 vector like this and do one of those, this is sort of taking me along the plane, and that'll take me to the point 8331 because I've only did 3, 0, and 1 onto 530, and that's the point where s is equal to 1 and t is equal to 0. And if I draw the other vector, the 1, minus 2, 2 like this, in nice green, that takes me to the point 913 because I'm adding a 1 and a minus 2 and a 2. And that's the point where s is 1 and t is 1. But at another t, another one of the 1 minus 2 2s, I get to 10 minus 1 5. So here are a load of points in the plane, and that's the point where s is 1 and t is equal to 2. Now, if I want the Cartesian equation for this plane, I need a perpendicular vector. So a vector that's at right angles to the plane. And the easiest way is using the cross product, which isn't in our content, but might as well use it. You can do it on the calculator with the multiplication button. So I do the cross product of 301 and 1 minus 2, 2, because this is going to be perpendicular to both these vectors. Now the easiest way to get the cross product is do the determinants of those bottom four. Now the determinant, of course, of these four, we just do AD minus BC. So I do the same with this. So I've got nothing minus 2, which gives me 2 up here. So this point, this component is going to be the determinant of these four. And then to get the next component, I'll do the determinant at the top and the bottom, so I'll knock out the middle, which so will be 6, then take away 1, gives me 5. But the middle one, I've got to stick a minus sign in front, just because well, that's life. And to get the bottom one, I'll do the determinant of these four at the top, so minus 6, minus 0, which is minus 6. Some people like to do this with it, the 3 by 3 determinant with I, J and K, with 301, 1 minus 2, 2. And of course the 3 by 3 determinant, you do the I and the determinant of those, and then minus the J times the determinant of the 3 and the 1 and the 1 and the 2. Okay, you could even write as a column vector like this, but that's a bit messy. So I think this is probably the easiest way to do it. If you've got your calculator, I don't know. And of course, what we found is a perpendicular vector to 301 and 1 minus 2, 2, and you check it. If we do the dot product, we'll get 6 and a minus 6 gives me 0, and then we'll have a 2 and a 10, give me 12, and a minus 12, and they'll give me 0. So I've found a perpendicular vector. You've also got to be able to do the old-fashioned way, without using the cross product. By saying the perpendicular vector, we'll call it x, y, and 1, because we can sort of scale it down. All we're bothered about is a vector in that direction, so we can make wherever the z component is, we can make it 1 by divided. So we call it x, y, and 1, and we know that it's perpendicular to both these two vectors. So when I do the dot product of these two, I get 0 for both of them. This one just gives me 3x plus 1 equals 0. This one, a bit more complicated, x minus 2y plus 2. But this gives me the x component minus a third. Sticking that in gives me the y component, gives me 5 over 6. So that perpendicular vector is going to be a multiple of this. And actually, if I do multiply all by 6, I get minus 2, 5, 6. So that's my perpendicular vector. That means the plane then is of that form. Any position vector of any point, if I dot it with that perpendicular vector, I always get the same amount. But I need to find out what that amount is. So I'll stick 5, 3, 0 in. And when I dot that with the perpendicular vector, that'll give me the D. So I'll have minus 10, 15, and 0 gives me 5. So that's the sort of the dot product equation of the plane. Not the Cartesian yet. And check it. I do 8, 3, 1. My other point. If I dot that with the minus 2, 5, 6, I'll have minus 16. And 15 and 6 does give me 5. If I dot the 9, 1, 3, I should get 5 as well. Minus 18 plus 18 and then 5. And another point 10 minus 20 minus 5 plus 30 does give me 5 as well. So this is my sort of r dot n form equation of the plane. But I want the Cartesian form, sort of the x, y, z form. But the r is just, well, it's the coordinates of the position vector, so I can put x, y, z as the r, and then I'll do the dot product with the perpendicular vector, put equal to 5, and I get minus 2x plus 5y plus 6z is equal to 5, and that's the Cartesian equation of the plane. Now, so it gives me another vector, another plane now. This one, I want to determine a vector equation of the line of intersection. So here's my other plane, and I need the equation of that line, the vector equation of that line. So here's the equation of that plane, which means I've got a perpendicular vector, which is that 5 minus 2, 3. That's the Cartesian form, of course. 5x minus 2y plus 3z equals 1. Now the vector equation of the line is going to look like this. I need a vector that takes me onto the line, and a vector that takes me along the line and in the direction of the line. Here's the origin. I could find 2 points on the line and use this one for the position vector of the line, and then use this vector. So I'll say that is the position vector of that point. That's the vector that takes me onto the line, and then I need this directional vector, which I'd have to do the difference between these two position vectors, which is that one. But I don't need to do that, because to find this directional of the line, it's going to be perpendicular to both these two, because this is perpendicular to this plane. This vector, this directional vector, is going to be perpendicular to both of these perpendicular vectors, which means I can do the cross product. And when I do it, I get, looking at the bottom 4, I'll get 15 minus 12 is 27, etc. Or even, I could simplify, because I just want a directional vector, so I can sort of scale it down, divide it all by 3. So I can use that as my directional vector. But I still need a point that gets me onto the line. Now the thing is, if we think about the plane as z equals 0, x and y can be anything, but any line that's not parallel of that is going to hit z equals 0. So if I've got a line in 3 dimensions, it's going to hit z equals 0. It's also going to hit x equals 0 and y equals 0. This is the plane x equals 0. So my line is at some point is going to have x equals 0. So if I'm going to find a point that point on the line, I can just put x equals 0, because at some point the x is going to be 0, and just solve these two simultaneous equations. If I'll do the first one minus 2 twice the second one. It'll get rid of the z's. So we get 9y equals 3. So y is a third. And then I need to sub it back into my original equation. The x is 0, y is a third to find the z value. Put in the first one, I'll have 2 lots of 0, 5 lots of a third, 6z. It's going to go just here. So that's my equation of the line of intersection of the two planes. And then it says use the answer to part B to determine the coordinates point of intersection of all three. So it gives us this new plane in Cartesian form. Now the temptation is, because you've got three equations now, 3 planes, 3 simultaneous equations, 3 variables, you could just stick it in the calculator. But it says use the answer to part B. And if you didn't use part B, well, you didn't get any marks for this question. So we've got to use part B. Now here's the equation of that line of intersection. That's the answer to part B. So I can write it as the R is x, y, z, the x coordinate, y coordinate, the z coordinate is going to be 9 lambda, a third plus 12 lambda, 5 over 9 minus 7 lambda. And I can find out where it hits this plane just by subbing the x, y and z into here, which will give me the lambda. So I've got 4 lots of 9 lambda minus 3y, which is a third plus 12 lambda, and then the minus the z. That's going to be equal to 0 because that's what it says. And if I sort of multiply it all out and solve it, these 36 lambdas go. I'll have 7 lambda is 1 plus 5 over 9, 14 over 9. So the lambda is 2/9. And then it's just a question of just sticking it into here to find out what the coordinates are. So 9 lots of 2 over 9, a third, and 12 lots of 2 over 9. And this actually gives me 2, 3, minus 1, which is handy. And one of the coordinates, now I don't think they'd be funny about this, they'd probably accept the position vector, but strictly speaking, you should write the coordinates like this. This is a vector, and this is the coordinates of that point. Is equal to 5, and that gives me z is 5 over 9. So this is the position vector of that point on the line.